Hello, I am Anirban Majumdar. Today I will be talking about synthesizing safe coalition strategies. This is a joint work with Nathalie Bartram from INRIA REN and Patricia Boyer from LSV. I will start with a brief introduction to two-player concurrent games on graphs. This is a model of games on graphs where we are given a graph in the input and a finite set of actions sigma. So the edges of the graph are labeled with two length words over sigma. Now the game proceeds as follows. The game starts at the initial vertex, for example here at V0, which is denoted with a red token. Then the players choose the actions simultaneously, and then the next vertex is determined by their chosen actions. For example here at V0, if the first player chooses B and the second player chooses A, then the word formed is BA and the game will go from V0 to V1. Similarly, at V1, if the first player chooses A and second player chooses B, or vice versa, in both the cases, the word formed is either AB or BA respectively. And in both the cases, the game will move from V1 to V2 and so on. We say that player 1 wins the game if he can ensure his win against any strategy for player 2. Examples of winning objectives are reachability, safety, etc. So here is an example which we can model using two-player concurrent games. So this is an example from the paper of Alfred Hinzinger and Kupferman from 2007. Here, player 1 wants to reach home safely, where player 2 wants to throw a snowball at him. So in the picture, the initial state is V0 and player 1's target vertex is to reach V2. For example, at V0, when player 1 hides and player 2 waits, the game remains at V0. As another example at V0, if player 1 runs and player 2 still waits, then the game goes to V2 and player 1 wins immediately, and so on. Here one can show that no player has a winning strategy in this particular game. In this work, we are interested in extending the two-player concurrent game in a parameterized setting, where parameter is exactly the number of players. Here again as input we are given a graph and a finite set of actions sigma. Now the edges of the graph are labeled with languages of finite words over sigma. Number of players is unknown and the game proceeds as follows. So the game starts at initial vertex. Here again, for example, suppose it's V0, which is denoted with a red token on it. Then adversary fixes some K, that is the number of players, and that K players choose their action simultaneously. And this form a word W, which is nothing but A1 up to AK. And the next vertex is such that this W belongs to Li. For example, at V0, if this W belongs to L3, then the game goes to V1. And from V1 again, if this W with K players belongs to L6, then it goes to V2 and so on. So here notice that we allow non-determinism between these languages. So this W can be in more than one language. In that case, the non-determinism is resolved by the adversary. In this parameterized arena, we are mainly interested in two kinds of decision problems. First, where a distinguished player is trying to achieve a goal against arbitrary number of opponents. And second, where arbitrary number of players are trying to achieve a common goal. So the first one has been shown to be decidable and was published in FSTDCS 2019. And we are mainly focused in the second decision problem in this work. So here I will define the safe collision problem formally. We are given a graph as input where the edges are labeled with regular languages over sigma. Then a strategy of player I is a mapping from sequence of vertices to sigma. And then a collision strategy is nothing but an infinite tuple over sigma i's. Equivalently, sigma tilde can also be written as a mapping from sequence of vertices to sigma power omega. Given an initial vertex V0 and a collision strategy sigma tilde, we denote by out k V0 sigma as the set of plays induced by this strategy sigma tilde from V0 when there are exactly k players. We say that the coalition wins the game if they can keep the play within a given safe set of vertices. So formally, input of the decision problem is an arena A, initial vertex V0 belongs to V, and a set of safe vertices which are denoted by green here, S. And we output yes if and only if there exists a coalition winning strategy. That is, if there exists a sigma tilde such that for any k, out k v0 sigma tilde is subset of s power omega. Let me now show an example. So this is the same example as in the previous slide. So here sigma is a comma b, and all unspecified transitions lead to a losing vertex bottom, which I have not shown in this slide, but it was shown in the previous slide. And the coalition needs to stay within the safe vertices, which are depicted in green. So here a coalition has a winning strategy. So coalition at V0 always plays A, B, A power omega, since any other choice would lead to bottom for some k. Now at V1, notice that the coalition has two choices, but depending on the history, it makes its choice. So if the history is V0, V2, V1, it infers that there is exactly one player. Hence, they choose B power omega from V1. On the other hand, if the history is V0, V1, then the coalition infers that there is at least two players and hence they choose A power omega. In case it loops to V0, it again chooses AB A power omega from V0. So this is a coalition winning strategy. In the rest of my presentation, I will show that the safe coalition problem is decidable. This is done in two steps. First, we reduce the parameterized arena into a finite tree. So this tree is nothing but an unfolding of the arena. Therefore, the nodes of the tree are labeled with the corresponding vertices and the edges are labeled with the corresponding languages. We terminate a branch if either of the following happens. So either if some label repeats in the same branch, or if the label does not belong to S. The idea behind the stopping criteria is that if a vertex repeats in the arena A, then the coalition may take the same strategy as its first occurrence. Because if it ensures safety in the first occurrence, then also it ensures safety for the later occurrences. And this is the case particularly for safety objective. Now we have reduced the arena into a finite tree. I will define a game on this finite tree. So a coalition strategy in the tree is nothing but a mapping from internal nodes to sigma power omega. And we say that the coalition wins the game on the tree if they can reach a safe leaf, whatever the number of players is. Then we can show that the coalition has a winning strategy in the arena if and only if the coalition has a winning strategy in its unfolding tree. The idea behind the proof is as follows. Any node in the tree corresponds to a finite history in the arena A. Moreover, any history in A uniquely maps to an internal node in tree. Therefore, safe coalition problems actually reduces to existence of a winning coalition strategy in the safe coalition game in the finite unfolding tree. Now, we will show how to decide the latter problem. So here we give an express algorithm for the safe coalition problem. Suppose M is the number of internal nodes in the tree unfolding and R is the number of edges in the tree unfolding. Recall that a coalition strategy in tree is nothing but a mapping from internal nodes to sigma power omega. Equivalently, it can be written as an M tuple of omega words. Again, equivalently, it can be written as an omega word over sigma power M. Now we construct a safety automaton B over the alphabet sigma power M that runs the automaton on the edges in parallel. A global state in B is an R tuple of local states. Each component corresponds to one edge, and a state corresponds to different branches in the tree. We say a state in B is accepting if the corresponding branches reach safe leaves in the tree. And then we say that a run in B is accepting is every state in the run is accepting. Then we can show that this automaton accepts words corresponding to the winning strategies in the tree. In other words, coalition has a winning strategy in the tree if and only if language of this automaton B is non-empty. Now see that M is of size exponential in the number of vertices, and R is also of size exponential in the number of vertices. Therefore, the size of the automaton is doubly exponential in the number of vertices. Therefore, we can decide the safe collision problem in exponential space, and which I have not shown here is that this problem, the safe collision problem, is p-space hard. So here I'll show an example of the construction of this automaton. So this is the tree from the previous example, and these are the automata for the languages on the edges. Now let us construct the automaton B. So the initial state of B is a R tuple of states where each component is its own initial state. Then it reads a word in sigma power m and reaches another state. Recall that a state corresponds to some branches in the tree. For example, here the rightmost state corresponds to the green branch depicted in the picture. The green branch depicted in the picture reaches a safe leaf. That's why we mark this rightmost state green, that is accepting. Similarly, we construct other states. So here the middle rightmost state actually corresponds to both of the green branches shown in the picture, and both of them are accepting. That's why we say this state is accepting. This way we construct the whole automaton B. See that in this example the middle path in the automaton has all states accepting. That's why we say that language of this automaton is non-empty, which in fact corresponds to a winning strategy in the tree. Now I will talk about synthesizing a winning strategy. So one can not only decide the safe correlation problem, but also synthesize one if there exists a winning strategy in the arena. So if language of B is non-empty, then an accepting word of B will be of the form u v power omega. Then we define a strategy in the tree as follows. Lambda of node ni is the ith component of the word u v omega. That is lambda of ni equals to ui vi omega. And one can show that this lambda is actually a winning strategy in the tree. Then it remains to transfer this strategy to a winning strategy in the original arena. Recall that any history v plus in the arena uniquely maps to an internal node in the tree, which we denote by zip. Then define the strategy in the arena as follows. So sigma tilde of h is defined as lambda of zip of h. So given a history h, zip of h maps the history to the corresponding internal node, and then sigma tilde assigns the lambda of that corresponding node. Then one can show that this sigma tilde is actually winning strategy in the game G. Therefore, synthesizing winning coalition strategy is also in X space. Here I also like to mention that notice that this sigma tilde uses memory of size exponential in the number of vertices. And we can show examples where this bound on size of memory is unavoidable. Let me now conclude my presentation. So we have defined parameterized concurrent game arena, and we have defined coalition problems on this parameterized concurrent arena with safety objective. We have shown that safe coalition problem is decidable in exponential space. This is done by first reducing the coalition problem to a coalition problem on its finite tree unfolding, and then by constructing a doubly exponential size safety automaton, and then by checking the non-emptiness of the safety automaton. We have also shown that the safe collision problem is piecewise hard. Moreover, synthesizing a winning strategy, if exists, needs exponential space, and a winning strategy, if exists, needs exponential size memory, which is unavoidable. As a future work, we are interested in closing the complexity bounds that we have achieved here. Another interesting direction would be to investigate the coalition problem when the winning objective for the coalition is given by a reachability objective. For example, here in this picture, the game starts at V0 and the coalition can win if they can reach the vertex V1, whatever be the number of players is. So they can reach the vertex V1 only if the last player plays a B. Now they do not know how many players are there, but they still have a winning strategy in this particular example, that is player I plays B at ith round and play A otherwise. So for example, at the first round the coalition will play B A power omega. If there is only one player, then it immediately reaches V1. Otherwise, it loops in V0 and the coalition infers that the number of players is not equals to 1. In the second round, they will play A, B, A power omega. Similarly, if the number of players is 2, then the game immediately goes to V2. Otherwise, it loops and the coalition infers that the number of players is not 1 and not 2. So this way they can proceed, and whatever the number of players is after k rounds, whatever the number of player k is after k rounds, they reach the vertex V1. We are interested in investigating this problem for reachability conditions. Thank you.